In this video, we're going to solve a second-order differential equation using 4 different approaches. Right, so the first approach we're going to use is the method of undetermined coefficients. With all these approaches, in this video, we're not going to be going into any detail with each approach because the detail to these approaches is covered in separate videos in the playlist. So if you need to refer to any of them, then there are separate videos for this purpose. Okay, so starting with the method of undetermined coefficients, the first thing we're going to do is establish the auxiliary solution and find the solution to the homogeneous differential equation, which is the complementary solution, right? So the general solution will be the sum of the complementary solution and the particular solution. So the first thing we do is establish the auxiliary equation, which is m squared minus 4m plus 4 equals 0. So m minus 2 times m minus 2 equals 0. M equals 2 is the roots, right? We have equal roots, we have one root here. So the complementary solution will be c1 e to the 2x plus c2x e to the 2x. Because we have repeated roots, we have the presence of this x in our complementary solution. Now when it comes to determining the particular solution for this differential equation, we always look at the right-hand side, which we can call g of x, and we establish a particular solution that is of this form. So this is of the form a e to the 2x. But we cannot use a e to the 2x as a particular solution because e to the 2x appears in our complementary solution. We also cannot use ax e to the 2x because x e to the 2x also appears in our complementary solution. So now we are going to try and assume a particular solution of the form ax squared e to the 2x. Okay, so the particular solution form will be ax squared e to the 2x. So y prime will be, take ax squared as our first function f and e to the 2x as our second function g. Then using the product rule, the derivative of y will be f prime g plus g prime f. So the derivative of ax squared will be 2ax, and then we multiply by e to the 2x plus ax squared is now the constant, and the derivative of e to the 2x will be e to the 2x times 2, because 2 is the derivative of 2x. So just tidying that up, we'll have 2ax e to the 2x plus 2ax squared e to the 2x. Okay, so the second derivative, y double prime, 2a is a constant, so we'll just take that out. The derivative of x is 1 times e to the 2x plus, now x is held constant, so we'll have 2ax, the derivative of e to the 2x is e to the 2x times 2 plus 2a is a constant. The derivative of x squared is 2x, and then we multiply by e to the 2x plus, now 2ax squared is all constant, so 2ax squared, and the derivative of e to the 2x is e to the 2x times 2. So just cleaning this up, the double derivative is 2a e to the 2x plus 4ax e to the 2x plus 4ax e to the 2x plus 4ax squared e to the 2x, which will just simplify to 2a e to the 2x plus 8ax e to the 2x plus 4ax squared e to the 2x. Okay, we can then sub these three expressions into the differential equation. So we'll have 2a e to the 2x plus 8ax e to the 2x plus 4ax squared e to the 2x minus 4y prime, which is 2ax e to the 2x plus 2ax squared e to the 2x plus 4y, which is ax squared e to the 2x, and that equals 6e to the 2x. Okay, so that all simplifies to 2a e to the 2x equals 6e to the 2x. Comparing the coefficients now, 2a equals 6, which means that a equals 3. So the particular solution is therefore 3x squared e to the 2x. The general solution of this differential equation is therefore the sum of the complementary and the particular solution. So y equals c1 e to the 2x plus c2x e to the 2x plus 3x squared e to the 2x. So the annihilator method, we're looking at the right-hand side of the differential equation, and we need to find an operator that will annihilate this function 6e to the 2x. So the operator that annihilates functions of this exponential type are d minus alpha to the n. In this case, n equals 1, and alpha, which alpha is the coefficient of the exponent. It's the coefficient of 2x, so alpha equals 2. So the operator that will annihilate the function 6e to the 2x will be d minus 2. So as with the complementary auxiliary equation, we're just going to be writing, instead of writing it in terms of m, we're going to be using the operator d. So we're going to start off with d minus 2 because this operator will annihilate 6e to the 2x. So we'll have d minus 2 times, and then for that part of the differential equation, we'll have the operator d squared minus 4d plus 4, and this will equal 0. So we'll have d minus 2 times d minus 2 times d minus 2. There's one root here, so that root will be m equals 2, m equals 2, m equals 2. So the solution will now be the first constant c1 e to the 2x, but because we have repeated roots here, we can't have the same function again. So it'll be c2x e to the 2x plus c3x squared e to the 2x. Okay, the complementary solution is the same. We're dealing with the same differential equation here. So this part of the general solution is the complementary solution. So this part is y sub c, which means that c3x squared e to the 2x is our particular solution. So now we're going to use the particular solution and proceed as we did before by finding y prime and y double prime. So y is the particular solution, c3x squared e to the 2x. So y prime, c3 is a constant. The derivative of x squared is 2x, then we multiply by e to the 2x, and then we add c3x squared is all constant now. The derivative of e to the 2x is e to the 2x, and then we multiply by 2. So y prime will be 2c3x e to the 2x plus 2c3x squared e to the 2x. And then y double prime, substituting y double prime, y prime, and y into the differential equation will give us 2c 3e to the 2x equals 6e to the 2x. So comparing the coefficients, 2c3 equals 6, and therefore c3 equals 3. So the general solution to this differential equation is given by y equals c1 e to the 2x plus c2x e to the 2x. c3 equals 3, so we have plus 3x squared e to the 2x, and this is the same general solution we got for the differential equation when we used the undetermined coefficients method. Yeah, the third approach to solving this differential equation is using the method of variation of parameters. So we're not going to go through the complementary auxiliary equation again because it's the same differential equation. So it's the same complementary solution. So we're going to go straight into the particular solution. So with variation of parameters, our particular solution is of the form u1 y1 plus u2 y2. Now I'm abbreviating these just for simplicity's sake. It's really u1 of x, y1 of x plus u2 of x, y2x. So we're just abbreviating it like this. So the solution, again, the detail to the variation of parameters is covered in a separate video. So we're not going to go into the detail of how we got to the solution. We're just going to go straight into it. So the u sub 1 prime is given by the Wronskian sub 1 divided by the Wronskian, and u sub 2 prime is given by Wronskian sub 2 divided by Wronskian. Now the Wronskian is determined from the complementary solution. So e to the 2x is the first solution, y1, and x e to the 2x is the second solution, y2. So we're going to take the Wronskian of e to the 2x, x e to the 2x, and that equals the determinant of the first row is e to the 2x, x e to the 2x, and then the second row will be the derivative of these functions in the first row. So the second row will be 2 e to the 2x. That'll be the first entry in the second row. And the second entry in the second row will be e to the 2x plus 2x e to the 2x. Okay, so that equals the determinant of this matrix will be e to the 2x times e to the 2x plus 2x e to the 2x minus 2 e to the 2x times x e to the 2x. So that's e to the 4x plus 2x e to the 4x minus 2x e to the 4x, and that simplifies to e to the 4x. So this is now the Wronskian. Wronskian sub 1 is the determinant. The first column will be 0, 6 e to the 2x. So Wronskian sub 1 will be, the first entry will be 0, so it will be minus 6 e to the 2x times x e to the 2x, which is minus 6x e to the 4x. So that's Wronskian 1. And then Wronskian 2 will be, so Wronskian 2 will be e to the 2x times 6 e to the 2x is 6 e to the 4x, and then we're subtracting 0. So we have Wronskian 1 and Wronskian 2. So u sub 1 prime is given by Wronskian 1 over Wronskian, which is minus 6x e to the 4x over e to the 4x. So u sub 1 prime will be minus 6x, and then u2 prime will be Wronskian 2 divided by Wronskian, which is 6 e to the 4x over e to the 4x. So u2 prime will be 6. We're now going to integrate both of these expressions. So on the left we'll have u1 equals minus 6 x squared over 2. So u1 will be minus 3x squared, and u2 will be 6x. So the solution, the particular solution, is u1 y1 plus u2 y2. u1 is minus 3x squared, y1 is e to the 2x, plus u2 is 6x, and y2 is x e to the 2x. So the particular solution is minus 3x squared e to the 2x plus 6x squared e to the 2x. So the particular solution is 3x squared e to the 2x. So the general solution is therefore given by c1 e to the 2x plus c2x e to the 2x plus 3x squared e to the 2x, which is the same solution we got when we used the method of undetermined coefficients and the annihilator method. The final approach we're going to use is Laplace transform, and with this differential equation we've got added initial conditions. So the Laplace transform, we're going to take the Laplace of every single term in the differential equation. Each constant we can actually just pull out of the Laplace transform. The Laplace transform of y double prime, the expression is s squared y of s minus s y of 0 minus y prime of 0. The Laplace of y prime is s y of s minus y of 0, and the Laplace of y is just y of s. So substituting these expressions here into the differential equation, we have s squared y of s minus s y of 0 minus y. This is actually supposed to be prime of 0 minus 4 times y prime, so it's 4 times y of s minus y of 0 plus 4y of s, and that equals, now the Laplace of 6e to the 2x equals 6. I'll just write this with the 6 outside the brackets first, equals 6 times 1 over s minus 2. So it's going to be 6 over s minus 2. Okay, so now we're going to use the initial conditions given here. So we'll have s squared y of s minus s. Y of 0 is 4. So 4 times s, we're just going to write this as 4s. Minus y prime of 0. Y prime of 0 is 7. So minus 7 minus 4 times s y of s minus y prime is, y of 0 is 4 plus 4 y of s equals 6 over s minus 2. So cleaning that all up gives us s squared y of s minus 4s y of s minus 4s minus 7 plus 16 is plus 9 plus 4 y of s equals 6 over s minus 2. Now just taking each term with a y of s, we will have s squared minus 4s plus 4 times y of s minus 4s plus 9 equals 6 over s minus 2. Okay, getting an expression for y of s, we will have 4s minus 9 over s minus 2 all squared plus 6 over s minus 2 all cubed. We're just dividing through by s squared minus 4s plus 4, which is s minus 2 all squared. So we're dividing 4s minus 9 by s minus 2 all squared, and we're dividing 6 over s minus 2 by s minus 2 all squared. So we have s minus 2 all cubed in the denominator of the second fraction. This simplifies to 4s squared minus 17s plus 24 over s minus 2 all cubed. From here, we're going to need to use partial fractions to get this expression into a form that we can then apply the Laplace transform to. We're not going to get into detail of partial fractions in this video because there is another video in the playlist that covers partial fractions in detail. So decomposing this expression into partial fractions gives us 4 over s minus 2 minus 1 over s minus 2 all squared plus 6 over s minus 2 all cubed. Taking the inverse Laplace transform of each of these expressions, so applying the inverse Laplace transform to this expression, we're going to get y of x equals, and we're not going to go into detail as to how we got these solutions because this is covered, the detail is covered in another video, in the same playlist. So y of x equals 4e to the 2x minus x e to the 2x plus 3x squared e to the 2x. Now this looks different to the general solution we obtained for this differential equation using the other three methods, and that's because we have it's an initial value problem. So if we apply these initial conditions to the solution we obtained previously, we're going to get this solution over here. So we're actually going to do that. Okay, so this expression here is the solution we got with the three previous approaches. We're now going to apply these initial conditions to this general solution. So when x equals 0, y will be 4. So 4 equals c1. X is 0, so we'll have e to the 0, which is just 1. X equals 0, so this term is going to fall away, as is that term going to fall away. So c1 equals 4. And then applying the second condition, so this will be the derivative of this general solution. So we're going to first need to get the derivative of this. So y prime will be 2c1 e to the 2x plus c2 e to the 2x plus 2c2x e to the 2x plus 6x e to the 2x plus 6x squared e to the 2x. So applying the second condition now, when x equals 0, y prime of 0 will be 7. So 7 equals 2, c1 is 4, and x is 0, so we'll have e to the 0, which is just 1, plus c2 times 1, and when x is 0, then these terms are going to fall away. So we'll have 7 equals 8 plus c2, so c2 is minus 1. So now the general solution is y equals c1 is 4 e to the 2x, c2 is minus 1, so we have minus x e to the 2x plus 3x squared e to the 2x, and this is the same solution that we got using Laplace transform.